Hello and welcome to the next of the lectures under the series titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last few lectures, we have been discussing the construction of fuzzy implications, specifically their construction from other fuzzy logic connectives. We have already seen the family of SN implications which are obtained from a T-conorm and a negation. We have had a gentle introduction to the family of R implications which are obtained from just T-norms. In this lecture, we will further study R implications vis-a-vis how to obtain their formulae for yet another T-norm and also the properties that they satisfy. We will also look into the third and final family of fuzzy implications using this construction in this lecture series, that of QL implications. Let's have a quick recap of R implications. We have seen that P implies Q in the classical logical setting can be equivalently represented by the formula negation P or Q, from where we obtained our inspiration for the family of fuzzy implications. Writing it in terms of its set theoretic equivalence, we have seen that A implies B can also be represented as A complement union B. Staying in the set theoretic framework, we have seen that this could also be equivalently written as the largest subset C of X such that A intersection C is contained in B. Now, moving back to the language of lattices, importing it there, we see that P implies Q can be written in this equivalent form. We took our inspiration for the family of R implications from here, and as we saw, it is the meat that is playing an important role here, the conjunction, which at first cut has been generalized to that of a T-norm. Hence, given a T-norm, we could define this function which we denote as IT. IT of xy is equivalent to the supremum of all those t such that t of xt is less than or equal to y. Now, it can be shown that every such function is in fact a fuzzy implication. In the last lecture, we have seen that if you fix an x and y from 0, 1, then the implication itself can be decoded into the following simpler form. You can look at the set AXY. XY is for this fixed pair x comma y from 0, 1. AXY can, if you denote by AXY, the set of all t such that t of xt is less than or equal to y. Clearly, IT of xy is actually equal to the supremum of the set. Using the properties, especially the monotonicity of a T-norm, we have seen that the set AXY for a fixed xy can either be the closed interval 0t or the closed 0 open t interval for some t belonging to 0, 1. We have also seen that, or at least we have noted that these basic implications, fuzzy implications of Gödel, Goguen, Lukasiewicz, Fodor and Weber, they actually belong to this family of R implications. In the last lecture, we have seen how to obtain the Gödel as an R implication from the minimum T-norm. In this lecture, let's take up one more such T-norm, maybe that of the product T-norm, and we will go ahead to show that the Goguen implication can be seen as an R implication obtained from the product T-norm. Once again, let's recall. This is written or can be written as AXY. Note that AXY is set of all t in 0, 1 such that t of x comma t is less than or equal to y. Since in our case t is tp, that is t of xy is equal to tp of xy is equal to xy. Now for any arbitrary xy, if you were to write AXY, this is a set of all t element of 0, 1 such that x into t is less than or equal to y. Now once again, Given any xy, we can consider two cases. Case 1, x is less than or equal to y. We have seen already that in this case, for the Gödel implication, it of xy is actually equal to 1. In fact, this is true for any t norm t. Why is it so? Let's consider an arbitrary t, and what we want is t of xt to be less than or equal to y. Now we know that for any t, t is always less than or equal to minimum, because minimum is the largest t norm. So now that means definitely this is less than or equal to x. Now this is less than or equal to y, no matter what the t is. In fact, since x is less than or equal to y, t of x1 is equal to x is less than or equal to y. So this implies 1 itself belongs to axy. This implies axy is in fact 0, 1, implies supremum of axy is equal to 1 is it of xy for any t norm t. Of course, please note we are operating under the assumption x is less than or equal to y. Now consider the case x greater than y. So in this case, let's look at axy. There is set of for t element of 0, 1, and for the product t norm, it is xt less than or equal to y. Note that x is greater than y, and now we want the maximum such t, supremum of all those t such that xt is less than or equal to y. This could also be written equivalently as t less than or equal to y by x. Note that x is greater than y, which means y by x, the value it can take is strictly less than 1, and from here it is clear that supremum of axy is actually equivalent to y by x. If we were to look at it like this, we have 0, 1 here, and y here and x here. If you're asking the question, what is that t that we can go up to such that t is actually that value, maximum of all the t's such that t of x t comma t is less than or equal to y. So clearly for the product t norm, the maximum t that you can get is y by x. So if you were to put these two together, for the product t norm, what we have is this: 1 if x is less than or equal to y, and y by x if x is greater than y. Now there is nothing but the Goguen implication as we know it. Well, let's look at discussing the desirable properties of the family of R implications. Once again, let's recall that we have these 4 properties: the left neutrality property, or just the neutrality property, which talks about if x is equal to 1, then the implication should take the value that is in the second argument. That means I of 1 comma y should be equal to y. Geometrically, we know that it is restricting the right boundary to that of the identity function. The identity principle talks about what happens to the graph of the implication, fuzzy implication, when you walk along the diagonal. The ordering property talks about when it can be 1. It can be 1 because of the monotonicity of fuzzy implication. If it has IP, then whenever x is strictly less than y, also it is 1. But ordering property precludes it from having the value 1 when x is greater than y. And finally, the exchange principle, as we all now know it, allows you to exchange the arguments x and y in this equation. Let's look at the graphs of some R implications and also discuss the desirable properties. If you look at the Gödel implication, This is what we have obtained. It is the R implication obtained from the minimum T norm. We see that it has the neutrality property, it has IP, in fact it has OP, ordering principle, and it can also be shown that it does have the exchange principle. If you look at the natural negation, it is the smallest fuzzy negation. At 0 it is 1, and at every other point it is 0. So is the case with Goguen implication, which, as we have just seen, is the R implication obtained from the product T norm. Its natural negation is the smallest fuzzy negation. It has NP, it has IP, and also OP. It can also be shown that it satisfies the exchange principle. These are again our basic fuzzy implications, the Fodor's and Lukasiewicz fuzzy implications. Once again, both of them satisfy OP and hence IP also. They satisfy neutrality property, and interestingly, their natural negation, as you can see, is actually 1 minus x. Please recall that both the Fodor and Lukasiewicz fuzzy implications are also SN implications. However, neither the Gödel nor the Goguen implication is an SN implication. This is the Weber implication. You will see that it has the neutrality property. Its natural negation is the largest fuzzy negation. It has IP but not OP. It doesn't have the ordering property because even when x is greater than y, it has the value 1. Now if you are wondering to which T norm or from which T norm can we obtain this as an R implication, it is the drastic T norm. If you take the drastic T norm and use the formula IT, the corresponding R implication that you would obtain will be the Weber implication. Well, and geometrically we have seen when a fuzzy implication has an IP or OP, especially R implication. Now let's look at it a little more in detail. What is the natural negation of an R implication? Recall, given a T norm, this is how we define the natural negation of a T norm. The natural negation of a T norm is defined as all those T element of 0, 1 such that T of x comma T is equal to 0. Now, IT of xy is defined as supremum of all those T element of 0, 1 such that T of x comma T is less than or equal to y. And we know that the natural negation of an implication is nothing but I of x comma 0. So if it is IT, then it is IT of x comma 0. And what we get here is supremum of all those T element of 0, 1 such that T of x comma T is less than or equal to 0. We know that T is a mapping from 0, 1 square to 0, 1. So the smallest value it can take is in fact 0, which means this can only be equal to 0, which essentially says this is nothing but the natural negation obtained from the corresponding T. Now, what about the other properties? It can be easily shown that IT satisfies both the neutrality property and the identity principle. Why so? Let's look at IT of 1 comma y. Now T is any T norm, and this is the definition of an R implication. So you will see it is nothing but supremum of T element of 0, 1 such that T of x comma 1 comma T is less than or equal to y. We know that 1 is the neutral element of T norm. That means if you want this to be less than or equal to y, the maximum value, the supremum that T can attain is in fact T or in fact y, which means this is equal to y. Now what happens to the case IT of x comma x? Now there is nothing but, looked at another way, supremum of AXX. Now AXX is equal to set of all those T element of 0, 1 such that T of XX x comma T is less than or equal to x. Once again, making use of the fact that the 1 is the neutral element of a T norm, we have seen earlier too that the maximum value that t can go up to is 1. So this is actually equal to 0, 1. And so when talking about supremum, it is supremum of 0, 1 and it is equal to 1. From these two, it is very clear that any R implication satisfies both neutrality property and the identity principle. The question is, what about exchange principle or ordering property? Well, not all R implications do satisfy this. We have seen only the basic fuzzy implications, examples from basic fuzzy implications. Of course, all of them satisfy EP, but as you have seen, Weber does not satisfy OP. Now the question is, when do they satisfy this? In the case of exchange principle, the jury is still out there. People still work on it. It is not really nailed down. The properties on a T norm such that IT, the R implication obtained from T, does have the exchange principle. We know that those obtained from left continuous T norms definitely satisfy the exchange principle, but that is not necessarily the case. Okay. With respect to the ordering property, let's recall what we defined as a border continuity of a T norm T. We said a T norm is border continuous if it is continuous on the boundary of the 0, 1 square, on the unit square. Essentially, it means it should be continuous on this set. It can be proven that an R implication satisfies ordering property if and only if the T norm from which it is generated is border continuous. Now, without going into the proof of this result, which is quite involved, let's look at some examples. You might recall that this T norm is actually border continuous. Of course, clearly it is not continuous. There is a huge gap here. It is border continuous, but not continuous. Before looking at the corresponding R implication, let's only look at what its natural negation is. So for a T norm, the natural negation is the boundary of its 0 region. So you see that at 0 it is 1. Between 0 and 0.5 it is actually 0.5, and from 0.5 to 1 it is 0. So if you were to draw this, this is how it will look like. This is the natural negation of this T norm. Now, if you look at its corresponding R implication, we see that clearly it has OP, and what is interesting is the natural negation of that is at 0 it is 1, between 0 and 0.5 it is 0.5, and from 0.5 to 1 it is actually 0. That means the natural negation of the R implication, natural negation obtained from the R implication coincides with the natural negation obtained from the T norm. Now, this is a T norm which is not even border continuous, as you can see here. However, notice the natural negation of this T norm is between 0 and 0.5 it is 1, and after that it is 0.5, at 1 it is 0. If you look at the corresponding R implication, this is how it looks like. Since it is not border continuous, we do not expect it to be having the ordering property, which is also true. As you can see, it takes the value 1 here even though x is greater than y. However, what is interesting is the natural negation of this R implication. It is 1 till 0.5, and after that it is 0.5, and at 1 it is 0. Well, as was mentioned, R implications have had their origins at different source points. In the study of solutions of systems of fuzzy relational equations, R implications did emerge. Fuzzy relations and fuzzy relational equations will be taken up in the lectures given in the next week. It is sufficient to know that R implications have also had their origins, the study of such systems. In fact, Sanchez, way back in 1976, showed that it is essentially the greatest solution of the Suchman composition. That is where an R implication will raise its hood. It had appeared as the phi operator in the work of Petrich later on in 1982, and also as the alpha T operator in the work of Miyakashi and Chimbo in 1985. So you can see that over a period of a decade, from 76 to 85, different researchers have found that R implications emerge in different contexts. Finally, a word about the nomenclature. The term R implication itself is a shorter version of residual implication, but we should be very careful in using this. IT is also called as the residuum of T, but this nomenclature is valid only if the T-norm is a left continuous T-norm. The reason for this will be explained going forward, because only if the T-norm is a left continuous T-norm can we ensure that the T-norm T and the R implication IT, they satisfy what is called the residuation principle or residuated property, from which we get this term residuum or residual implication, whose shortened version is actually the R implication. Well, let's get back to what we started with. We know that P implies Q can be represented as negation P or Q in the classical setting. Using this, we moved into the set theoretic framework and said, okay, it could be also looked at as A complement union B. Later on, we further gave another equivalent definition in terms of finding the largest subset C of X whose intersection with A is contained in B. These two gave rise to the families of SN implications and R implications. Looking at this formula can also be equivalently written like this, as A complement union A intersection B. Now, this formed the inspiration for another class of implications, at least in the fuzzy logic framework. It is called the QL implication. Of course, these are generalizations coming from implications which are used in quantum logic. So now you see here, there are three different operations involved: the complement, union, and the intersection, which are typically generalized in the form of negation, T-conorm, and a T-norm respectively. So we start with these three operations, a T-norm, a T-conorm, and the fuzzy negation, and define a function I like this: S of nx, T of xy. And since this function is based on these three operators, T, S, and N, we often denote it as ITSN. While every ITSN satisfies the boundary conditions of a fuzzy implication and is also increasing in the second variable, the decreasingness of this function, so defined, in the first variable is not guaranteed. For instance, that it is increasing in the second variable can be seen quite immediately. If you fix an x, nx is fixed, x is fixed. So as y increases, t of x, y increases, s of nx, txy will also increase. So clearly it is increasing in the second variable. That this function satisfies the boundary conditions of a fuzzy implication can be quickly verified. But if you ask about the decreasingness of this in the first variable, well, that cannot be ensured. So this leads us to discussing this function in two different ways, as a QL operation alone versus a QL implication. What is the difference? QL operation does not satisfy decreasingness in the first variable. If you obtain an implication using this formula, we will call it a QL implication. If you only obtain an operation which is increasing in the second variable and satisfies the boundary conditions of a fuzzy implication, but not the monotonicity, then we say it is only a QL operation. Essentially, this always ensures QL operation, but what we are interested is in a QL implication. Once again, quite interestingly, you find that 5 among the 9 basic implications that we have seen are in fact QL operations. Some of them are also SN implication. In fact, all these 5 are indeed SN implications. Let's look at some near misses. That means those that give only QL operations and are not QL implications. So if you take this triple, minimum, maximum, and the usual classical negation, the function you obtain is this max of 1 minus x, min xy. Unfortunately, this does not turn out to be a fuzzy implication. Why so? Let's look at this formula. Equal to max of 1 minus x, comma, min of x, comma, y. So let's fix a y. Let's fix y to be 0.6 and take two values for x. x1 is equal to 0.5 and x2 is equal to 0.6. Now if you look at x1 comma y, this is max of 1 minus x1. Please allow me to write it directly. 1 minus 0.5 is 0.5 comma minimum of 0.5 comma 0.6 is equal to max of 0.5 comma minimum of this is 0.5, max of these two is 0.5. If you look at I of x2 comma y, this is max of 1 minus x, which is 0.4 comma minimum of x is 0.6 now, x2 0.6 comma 0.6, so this is max of 0.4 comma 0.6, which is 0.6. As you can see, as x increases for this particular function, I also increases in the first variable for a fixed y. Clearly, that means this function is not an implication, not a fuzzy implication, and hence we do not get a QL implication from this triple of functions. Let's look at some examples where we get QL implications. It is also very illustrative for the kind of implications that this family can throw up, and that we will see from its geometry, that means by looking at the 3D plots. So if we take this T column and the product T norm under the classical negation 1 minus x, it does lead us to a fuzzy implication. So this triple does indeed give a QL implication. The graph of it looks like this. As you can see, it has the neutrality property. Its natural negation is 1 minus x. It appears. It has identity property. So if you put y is equal to 0 here, then what we get is 1 minus x square, 1 minus x square, and under root x square is under root, so you will get 1 minus x, which is what is the natural negation of this fuzzy implication. If you take the same T column and the product T norm, but change the negation to 1 minus root x, this is the function you get, which is again a fuzzy implication, and the natural negation indeed will be 1 minus root x itself. If you consider any T norm and the drastic T column, that's the largest T column, and the classical negation, this is the implication you would get. As you can see, 1 minus x is the natural negation. It has a neutrality property. It is almost the Weber implication, except that the natural negation is redrawn to make it 1 minus x. If you consider the minimum T norm, the nilpotent minimum T column, and the negation 1 minus x square, we get a QL implication that looks like this. Once again, neutrality property is given. 1 minus x square is the natural negation. And what is interesting is it also has OP. If you take this triple, nilpotent minimum T norm, nilpotent maximum T column, and then classical negation, you get such a fuzzy implication. Once again, it has ordering property. And similarly is the case with this. Of course, it does not have the ordering property. It has IP, NP, and the natural negation is 1 minus x square. So if you were to ask in general, what are the properties it satisfies? It is clear that ITSM will always satisfy NP. What about the other properties? Identity, exchange, and ordering principle. Once again, these are very tough questions. There are some sufficient conditions and necessary conditions. Such results do exist, but a complete characterization of QL implication satisfying these properties is as yet unknown. And it is also clear that the natural negation that you obtain from a QL operation is in fact the negation that you use to obtain the QL operation in the first place. Well, with this we'll come to the end of discussing constructions of fuzzy implications from other fuzzy logic connectives. At least in this course, these are the three families that we are going to see in depth as being constructed from other fuzzy logic connectives. We have seen three such families, that of SN, R and QL implications, and we have discussed the properties that they satisfy. In the next lecture, we will look at yet another construction method of fuzzy implications, that of obtaining them from unary generators. Once again, a good resource for the topics covered in this lecture is that of the book on fuzzy implications. You could also refer to a more recent collection of research articles titled under Advances in Fuzzy Implication Functions, which also discusses some of the interesting problems related to R implications and QL implications, some open problems and problems that have been solved and problems that are yet to be solved. Glad that you could join us for this lecture. I'm looking forward to seeing you again in the next lecture. Thank you again.